This lesson is just a quick review of what we've done for forces, just to kind of put all of our lessons together and help you maybe collect all of the information that you need to complete your assessment. So we'll do one of each of the kinds of questions that you would see. Now, first of all, just a quick recap of Newton's laws. So everything in this section is built on these three laws. So you're going to come back to these on a regular basis. An object in motion will stay in motion, and an object at rest will stay at rest unless acted on by an external net force. What that means is if you have constant velocity, so constant velocity or zero velocity equals F net of zero. Okay, so if you have a constant velocity or zero velocity, F net is zero. If F net is not zero, then law 2 comes into play, and this is what happens when we have a force being acted upon it. So an unbalanced force results in acceleration. With an F net or a net force, the sum of the forces equal to the mass of the object times the acceleration. Acceleration is always the result of the sum of all of the forces. So if in a question asks you, what is the acceleration of an object? It's telling you indirectly, what's the net force? Find that first, then find acceleration. Okay. And then for 3, for every action, there's an equal in magnitude, opposite in direction reaction force. So an example of that would be an object sitting on a table. Okay, so if you have an object on a table, gravity pulls it down, but the table pushes up. Okay, those are equal and opposite reaction forces there. Because they're balanced, the object is stationary. This is a bit of an abstract law because there's a few things that kind of come into play with it. If you really want to nerd out, you can research some stuff on Newton's third law and really what are some of those equal and opposite reaction forces. We isolate the scenario just to the object so that we see acceleration, but sometimes they look at the big picture and how it relates to the forces and the rest of the universe and all of that kind of stuff, but we're just not going to go there. Okay, so we're going to keep it simple. Equal opposite forces. Most of the time, the forces you're looking at is balancing the downward forces and upwards forces on an object to find the normal force, or this is the force of the table would be the normal force acting on the object here. So a quick summary, this chart is absolutely fantastic for you to use as you complete your assessment. So you can use this to look back at. This is all of our equations. So gravitational force is just mass times the acceleration due to gravity. Every object experiences gravitational force so long as we're dealing with Earth. Frictional force is the force caused by roughness between two surfaces. It's always in the opposite direction of motion, and its formula is mu. So this is our mu is our coefficient of friction. So it'll always be that decimal number. That's our coefficient of friction. And then the normal force, or the force that's upwards between the two surfaces. Okay, so the force, the force that the bottom surface puts on the object, basically. Normal force is the balancing force that opposes gravity. So normal force is where we get Newton's third law, and it's always perpendicular to the surface, so straight up from the surface. It's not always equal to gravity, but sometimes it is. So you're going to have to be conscious of when it's equal to gravity and when it's not. We'll have an example of that in actually 2 examples of that in our review here. So you'll have a couple examples of that. The easy scenarios, you're going to find it's equal to gravity. And then as soon as we have an angle involved, normal force will change depending on gravity. Okay, so just keep an eye out for that. That's one that's a little bit tricky to think about. So one way to think of it, if you're lifting up on a table, but the table's not not off the floor, it's still sitting on the floor, but you're putting a force upwards on it, the floor has to put less force on it because you're taking some of the weight. So in that case, the normal force is the force the floor puts on it, which would be a little less. So it's one of those little quirky things that does come up in your assessment. So just watch for it. Think carefully when you're asked about normal force. Is it equal to gravity or do you have to adjust it? Remember, it's what balances the upwards and downwards forces if something's on a surface. Applied force, it's usually given to you in your question. Sometimes you're asked to calculate it once you know your net force, but that's just the force that, any force that you're pushing, like an engine thrust or pushing and pulling an object, that kind of thing. So it's probably one of the easier ones to find. And then net force is mass times acceleration, or it's equal to the sum of the forces. So oftentimes we have to use these two equations together. Okay, sometimes you have to find the sum of the forces first to find acceleration. Other times you use acceleration to find the net force and then find one of the missing forces. So two different ways to use it, but these two are often used together the same in the question. All right, so a couple of calculation questions just to go through here. Sorry about that. All right, so simple example. The first examples on your assessment are all the simple kind. Always start with a diagram first. So we have a 3.75 kg block pushed along a tabletop with a force of 45 newtons. Coefficient of friction is 0.65. We want to find the force of friction and acceleration. I usually try to ask questions with A, B's, and C's because those A, B's, and C's help make sure that you find all of the pieces and give you a little bit of extra scaffolding. If I just asked you to find acceleration, you might forget to find the force of friction. So it's trying to help you out a little bit so you don't get stuck. All right. So first thing I always start with ILEC boxes, as you'll have noticed from the other lessons. So 3.75 kgs for our box mass. Sitting on a surface. So I like to draw all the forces I think I might need in first. Even sometimes I don't need all of them, but I usually draw all the arrows in and then go back so I don't forget anything. So we have the force of gravity. We know the table pushes up, so we have force normal. We have a force applied. And opposite the applied force is going to be the force of friction. We don't necessarily know how long our arrows should be, but we know gravity and normal force should be equal, and force of friction and force applied, well, is you can just do a guess on those until you calculate. This is just a sketch, just to keep us working through the problem. I usually will calculate for almost every question we need the force of gravity. So I usually just jump in and I calculate that first. Mass times gravity. So, and I like to work close to my picture. So don't be afraid to do that. You can work together off to the side as long as I can find it. 3.75 kgs times gravity, which is 9.81. Multiplying those two together, let me flip to my page to where I've calculated the final answer here. Multiplying those two numbers together, you get 36.8 newtons. Now I realize in this question, 3 sig figs, 3 sig figs, 2 sig figs. I'm going to just keep an extra one until I get to the end. If you keep either 3 or 2, I would be quite happy, not going to deduct any marks for that along the way. So you're fine there. So when I look at this, the force of gravity is equal to the normal force because there's no other upwards or downwards forces on this object. So we can just transfer that right up to the top, right at the beginning. If there was a pole that was at an angle upwards, we wouldn't be able to move that right away. Now we can fill in some of our other forces. So we've dealt with our mass. It says we have an applied force of 45 newtons. So we might as well fill that in. Okay, so we've dealt with that piece of information. And we have the coefficient of friction, and the first thing asks us to find the force of friction. So this is really, right now we have all the pieces filled in that are required to find the force of friction. So the force of friction is the coefficient of friction times the normal force, which is equal to 0.65 times our normal force of 36.8 newtons. Now that we have that, we multiply them together. This is a fairly high coefficient of friction. This value, 0.65, means basically it's like saying 65% of the force of gravity is getting transferred into friction force. That's kind of what those coefficients mean. It's what percent of the force between the two surfaces results in friction. I read that one time and I thought that's a really interesting way to describe how the coefficient of friction works. I really like it. So I don't know if it helps you or not, but I find it an interesting way to think of it. So that gives us a force of friction of 23.9 newtons, or if you want to go to sig figs, since this is one of your final answers, 24 newtons. I'll just fill it in over here. If you're filling out an assessment for me, I'm perfectly okay with you filling everything in a picture. I would love it if you put your final answer, even if your work is shown elsewhere, pop your final answer somewhere close to the actual question, or just put a box around it and make it really clear so I can see which one is your final answer. It expedites grading a nice little bit. So we've got A calculated, we've done that. Now we want to find the acceleration. So the vertical forces are balanced, so there's no vertical motion. All of the motion is horizontal. So we just want to compare the two horizontal forces. The applied force is bigger than friction, so we know it's going to move. Well, how much force is left over after we've overcome friction? So our net force is equal to the forward force of 45 newtons minus 24 newtons, which is the force of friction, which gives us a net force equal to 21 newtons. So that's the overall force that the object is moving with. And this is where those two equations come in and they work well together. So the net force is mass times acceleration, which is equal to 3.75. We'll fill in 21 for the net force times acceleration, and we're just going to divide out that 3.75. Okay, so acceleration is equal to 21 divided by 3.75, which is 5.6 meters per second squared. And if you can't pop that close to your answer, just to throw a box around, it makes it really easy to find out where that target was. I'll pop it up here too. It's 5.6 meters per second squared. And if we really wanted to, we could ask you a question about, well, if that's the acceleration, how much faster would it be moving in 5 seconds or 10 seconds, that kind of thing. But we're going to leave those two chapters separate, even though they do belong together for the sake of time and what we're able to do for question complexity. So next we're going to analyze the forces in an example where we're pulling. And in this case, we're not just pulling straight like the last question. That would be an example of an applied force pulling perfectly horizontally. But at this time, we're going to add one extra complication. We've got an angle. If you remember from earlier, as soon as you see angles, you have vectors. So, well, let's fill all of our forces in that we know first, and then we're going to deal with our vector. So we know that this block is 210 kg. I'm just going to add to my picture rather than drawing a new one. The force that's at an angle, so this rope force is 2,400 newtons. Okay, we know that we have the force of gravity. And we know we're going to have to calculate that. That gets a guarantee because it asks us what's normal force in the first part of the question. So let's just calculate it right at the beginning. So 210 times 9.81 gives us 2060 newtons. Okay, so we have that right off the top. These already calculated, I don't really need to recalculate. Okay, now that we have that, let's calculate the next piece of information. So we'll fill in some more arrows. We have a normal force, but in this case, normal force is not the same as gravity because we have an angle here. So let's deal with our angle. If we take this force, it goes forward, pulls the block forward, plus it also pulls the block upwards, okay? So it's pulling that block in two directions. Because some of that rope supports the block vertically, that means that not all of the force of gravity is converted to normal force. We've actually taken some of that weight if we were the person that's pulling it. So we need to use our vectors. We need to find out what's the vertical piece of this And then we'll find out what's left over from gravity that we have to balance with the normal force. We'll also figure out how much of that force is pulling perfectly straight forward. So this is my opposite. And this is my adjacent. Other words I like to use for them, this is my force parallel. So that's parallel to the surface. And this is my force perpendicular to the surface. Now to quickly calculate those for us, so to figure out what the forces are, sine of 25 degrees is going to be equal to, well, hypotenuse we know is 2400, and sine, you think, remember SOHCAHTOA? Sine uses opposite, so opposite's going to be that force perpendicular. Okay, at this point, you should be able to rearrange that. I'm not going to go through the rearranging with you. The force perpendicular is equal to 1014 newtons. So that's our upwards force. That's this one. This force here is our adjacent force. Cosine uses adjacent. So cosine of 25 is going to be the force parallel divided by 2400. So force parallel is equal to 2175. Okay. So those are, now we have all of our force pieces plugged in that we know. So let's go back and figure out what's the normal force. So the normal force is the balancing upward force. So we have 2060 newtons down. We have already this upward force here. This is an up force of 1014. So normal force is what's left over. So this is going to be equal to the force of gravity minus any other upwards forces, which leaves us with a value equal to 1046 or 1046 newtons. Okay, so it's the balancing upward force. So that just finished, while we're here, that finished off calculating A for us. So 1046 newtons. The next one, it says we want to figure out friction. So the force of friction is in the other direction. Force of friction is mu Fn. So that's going to be equal to 0.19. So there's a very small amount of friction times 1046 newtons, which will give us a value equal to 199 newtons. So our coefficient of friction, we'll fill it in over here, 199 newtons. I think I might have repeated myself to do a pause there. Sorry about that. So that has B calculated. Last piece is to calculate C. What's the acceleration of the crate? Now things are looking a little bit messy right now. The vertical forces are balanced. So we know vertically we don't have to worry about anything. If we want to take a look at our picture, maybe make it a little more simple. Forwards, we have the forward component of force is 2,175 newtons. Friction is in the other direction, and it's only 199 newtons. The net force, we're only thinking of horizontal because everything else balances, is going to be equal to the difference between those two. So F net is equal to 2,175 minus 199, which gives us a value of 815 newtons. Now we can find acceleration. So F net equals mass times acceleration. So 815 is equal to 210 kgs times acceleration, divide both sides by 210. That is an A, not a G, sorry. And acceleration in this case is 3.9 meters per second squared. And if we've used our meters, kilograms, we're always going to end up meters per second squared. So I'll often leave out the units as I'm calculating just because it tends to make the page a little bit less messy, especially given I don't have two boards to scroll on the computer. All right, so that has all of our pieces calculated. The third example, maybe this is, I think this is the third example, is pushing on an inclined plane. It's really similar to the last one, so we'll do a quick run through of it, and then I'm going to do one with tension. A crate that weighs 1,200 pounds is being loaded on a ramp with an incline of 18 degrees. If the coefficient of friction is 0.14, A, how much force would be required to lift the crate without a ramp? B, how much force is required to push the crate up the ramp at a constant velocity? Well, if you're just lifting the crate without a ramp, all you have to do is overcome gravity. So that's an easy one to calculate. So this is just going to be Fg, which is equal to mass times acceleration. Now, if you were in class on Wednesday and you're just watching this for a review, you will remember I pretty well forgot to switch pounds into kilograms and was kindly reminded. So we're going to switch this over. 1,200 pounds divided by 2.2 is equal to 545 kgs. Okay, so that's what we're going to use for our mass here. 545 kgs times 9.81. That's meters per second squared. And filling all of that information in, you will get 5,346 newtons as the force of gravity. And that's the only force we have to overcome to lift it. We just have to be able to lift with more than gravity. Next part says, well, what about pushing it up a ramp? Pushing it up a ramp is where things get complicated. So let's label all of our forces because we don't have a whole lot of forces listed here for us. So we know that gravity always pulls down towards the center of the earth, okay? The normal force is always straight up from the surface. You'll notice gravity and normal force are not exactly opposite each other, so we know we're going to have to use trig. Our hint that we have to use trig is this 18 degrees that we have tucked in there. We want to know how much force is needed to push the crate up. So we're looking for what is the applied force. That's our question. But we know we have friction pushing, holding us back. Okay, so those are our forces we're going to have to calculate. Now, if you think of a ramp, part of the force of gravity holds the box on the ramp, part of the force of gravity pulls the box down the ramp. So we're also going to have to overcome the part of gravity that pulls the box down the ramp. We'll call this Fg parallel to the ramp. The normal force is the gravity force perpendicular to the ramp. So we need to figure out what's this component, and our 18 degrees always goes in on the top of the triangle closest to the box. We could do trig to prove that. We don't have time to do trig to prove that, so we're just going to trust it that that's where it goes. Use the pattern. Okay. I hate doing that, but sometimes that's what we have to do for the sake of time and what we're allotted. Let's do our calculation. First thing, let's calculate the perpendicular force of gravity. Let's calculate the force. We got the force of gravity. We can fill that in. I don't even have to calculate it. 5,346 newtons. Now let's calculate the perpendicular force of gravity. So this is my adjacent side, so it's going to use cosine because it's next to the angle. So the force of gravity is going to be my hypotenuse. That's the vertical arrow. So we're going to have cosine of 18 is equal to Fg perpendicular divided by 5,346, the force of gravity. Fg perpendicular. Now this ramp is not super steep, so that most of the force due to gravity should be in the vertical direction. Okay, so the perpendicular force of gravity, you should be able to rearrange to find that. It's going to be the number on the bottom. So the hypotenuse, 5,346 times the cosine of 18 degrees, you should get a value of 5,084 newtons. Okay. If we want the parallel force of gravity, it's opposite side, so it's going to use sine. So the sine of 18 is the force gravity parallel. That's the force that's pulling it down the ramp, divided by 5,346, and the force of gravity parallel is equal to, let me see here, 1,652. Okay, So we have all of our pieces here. Now we can find out how much force is needed to push. Should we have all of our pieces? We got one more piece to calculate. How much force is needed? I know how much force is holding the crate on the ramp, what part of gravity. So this is equal to Fg perpendicular, just a different sign on it. So it's going to be 5,084 newtons. Now that I have the normal force, I can find the force of gravity, or the force of friction rather. The force of friction is my coefficient times Fn, the normal force, and that would be 0.14 times 5,084, which is going to be 712. Okay, now we have all of our pieces. So how much force is needed to push the crate up the ramp at a constant velocity? So this tells me the net force has to be equal to 0. Okay, so the forces up and the forces down have to balance each other out. So we know that the net force is equal to 0, which is equal to the force applied minus the forces that are pulling it back down the ramp. So we're going to minus friction because friction's fighting us. And we're going to subtract the part of gravity that's pulling it down the ramp, which is this number here, the parallel, the part of gravity that's in the same direction as the ramp. So 1652, so 1,652 newtons. So the force applied is going to be equal to 712 plus 1652. You can do all the rearranging on that. Basically, we're just adding the two pieces together because when we take them across the other side of the equal sign, their signs will change, and that gives us a total of 6,058 newtons. If any of that isn't clear, you're not sure just because of the way I've done the negatives, please let me know. Another way I could have written them is F up the ramp has to equal F down the ramp. And if that's easier for you to think of, great, you can use that. That's the same as saying the net force or the overall force is equal to 0. So it's just another way to look at it. So we know we need a total of 6,058 newtons in order to push the crate up the ramp. And I know I haven't really nitpicked sig figs here. This question technically has 2 sig figs everywhere. So if you wanted to go to the proper sig figs, we would say 6,200 or 6,100 newtons instead of 6,058 newtons. So I've left the extra decimals, extra digits in there for now, but feel free if you're rounding. I will not penalize if you give me all of those. If you give me 20 decimal places, I'll say, hey, stop and think about your sig figs. I know, because that's way more than we would actually need to have. So don't sweat that too much. Just use sig figs to help you be reasonable in the numbers that you present. All right, last example. I did not do this one in class, but it is very, very, very similar to something on your assessment. So if you've patiently gone through this video, I am rewarding you with the steps for how to do one of your questions. I promised you I would do that. You probably found some of the other ones really helpful too. If the suspended object has a mass of 120 pounds, what is the tension in each of the cables if it's suspended with equal angles, each measuring 55 degrees? Got some kind of a glitch here in symbols. So we know this is 55 degrees, 55 degrees. We have an object. This is 120 pounds, which if we divide by 2.2 is equal to 54.5 kgs. Okay, we got to make sure we have our kgs. No, don't forget that. So we know gravity is pulling this suspended object down. Fg is equal to 54.5 times 9.81. Multiplying those two together, we get 535 newtons. So nice, easy. Gravity's easy. Everybody should be able to put gravity on their diagram. You'll get at least a half a mark or a mark for it, depending on how essential gravity is or how much of the calculation requires gravity. So just a little tip, by the way, if you're not sure of anything else, at least calculate gravity. You usually need it. Now, in this case, we don't have a normal force. The force that's upward balancing gravity comes from the tension in the rope. So this cable pulls upwards. It also pulls outwards. And this cable is pulling upwards. It also pulls outwards. Now, we're not worried about the outward forces. We're just wondering how much tension is in these cables. So we just need to know, well, how much upwards force does the cable have? So I can use trig to find the tension. So the upwards force, if each cable is pulling upwards, two cables, it splits gravity in half. So we know that the upward force, or I'm going to say half of the force of gravity, I'm going to do this in shorthand, is pulling upward in each rope. Okay, that's what it's equal to. Gravity pulls down, but because we have two cables, a force equal to half of gravity is pulling up on each cable. I know you can't see my hands moving. I'm just realizing that as I do some very animated descriptions here. So now that we have that, let's find out, well, what is half of gravity? So if we take our gravity, 535 newtons, and we divide it by 2, we get 265.75. Oops, 0.7. Oh, I flipped some numbers. I just had a dyslexic moment. If you're following along with your calculator, I might be going a little bit quick for you to punch things in. Feel free to just hit pause now and then to catch up. So 267.5. If I make enough mistakes writing, I'm slow down enough for you to fill in anyway. Okay, so that's the upwards force from gravity. So this goes 267. I can't seem to get those two numbers, 0.5 newtons. That's the upwards force. And in this cable, same thing. Okay, both of them have that much upwards force. So that balances out gravity. So we know that block is not going to rise or fall. It's holding steady. Well, how much tension is in the rope? Well, we got a simple trig question. Angle is here, opposite, hypotenuse. SOH, very first one, so sine. So the sine of our angle is equal to opposite over hypotenuse. Filling that in, you guys are experts on that from last semester. So the sine of 55 degrees is equal to 2067.5 newtons. Let me restate that, 267.5 newtons. I've been dealing with thousands up to this point and can't seem to get that word out of my head, divided by the tension in the cable. So that's this value. This is the question where people often make mistakes rearranging, but it's an easy one. We trade places. Tension is equal to 267.5 divided by the sine of 55. Putting that in, you get a total for tension of 326 newtons. I'm definitely having a dyslexic moment. Hopefully I haven't done that too many other places while we were going that I didn't catch. 326 newtons. Okay, so that's our final answer. The tension in each cable is going to be equal to 326. And this one would be 326. And depending as your angle changes, that amount of tension changes. And that's why for some of your classes, you'll look at rigging angles or lifting angles more than others, but that's why we like to keep those angles between 30 and 60 degrees. And you can do some calculations to prove why we would like that. Generally, you don't want the tension in the cable to be greater than the tension due to the force of gravity. Otherwise, it puts extra strain that isn't necessarily required. All right, so quick summary. Hopefully that wasn't too long for you, not too painful, but that should give you an excellent review for working through that assessment. You can hand it in person, or you can put it into Dropbox, depending on what your wishes are.